Hey everybody, my name is Chris and I'm a tutor here at Chegg.com, and I mostly do math and a little bit of computer science. And in this video, we're going to do an example of contour integration. So contour integration is a technique in complex analysis that helps us evaluate integrals, definite integrals, that we otherwise might not be able to evaluate. So here we want to evaluate the integral from minus infinity to positive infinity of cosine of x divided by x squared plus 1 dx. So if you're here watching this video, I'm assuming that you already know a little bit about contour integration, and maybe you're just here to see another example. So because of that, and in the interest of saving time, there will be some steps that won't fully be explained, and I won't fully explain all of the details behind everything that's happening. That would just make the video way too long, even for one example. Okay, so what we want to do, the idea with contour integration is we want to consider an integral that's very similar and going to be very helpful in the complex plane. So in this case, we want to consider the integral over some path gamma, capital gamma, and in this case, the function we want to consider is e to the I z over z squared plus 1 dz. Now, usually we want to replace all of our x's with z's, but if we do that with cosine, that'd be bad. Cosine of z is bad because this is unbounded. As z gets really large, as in farther away from the origin, as the modulus of z gets really large, that could be a problem for us. So we want to consider e to the iz instead because it's bounded. And that's going to be better for us. All right, now anyway, let's go ahead and draw a picture of what gamma is. So gamma, whatever we have for capital gamma, that's really going to depend on the specific problem. And in this case, our gamma is going to be the upper semicircle. So this is x, this is y. Gamma is the upper semicircle here. And we'll just pretend that that's a nicely drawn semicircle. So we'll call this capital R. This will be negative capital R. And then we're going to orient it counterclockwise, as we typically do. Okay, so, oh, and also one last thing. This the curvy part up here, I'm going to call that C. All right, so C just represents the curve, the actual arc up here. All right, now notice, and this whole thing is gamma, so the entire thing altogether is gamma. So the integral of this function over gamma is going to be the integral from minus r to r. And notice that as we go from minus r to r, we're actually on the real axis. In the complex plane, the x-axis is the real axis, so we can say e to the ix over x squared plus 1 dx. And then plus the integral over c. This, remember, c is the arc part right here. E to the iz, and then that's z squared plus 1 dz. All right, now what are we going to do? The idea is we want to evaluate this and evaluate this, evaluate this integral here, and then take the limit of both sides as r goes to infinity. Because as r goes to infinity, we're pretty much going to have this integral here, just a slight variation on it because of the exponential here, but we'll handle that when we get there. So first let's evaluate this on the left side there. So the integral over gamma of e to the iz, we're going to want to use residue theory for that. And again, we can't spend too much time on the details here, but basically this is 2 pi I times the residue of e to the iz over z squared plus 1 evaluated at z equals I. All right, so this function here has two poles, one at I, and there's another one at minus I. But positive I is the only one that's inside of the curve here, as once r gets big enough, which is definitely going to happen because remember, eventually we want to take the limit as r goes to infinity. So we are going to have I in here eventually. Okay, so this is going to be 2 pi I times z minus I times e to the iz over, and then let's go ahead and factor this. So z squared plus 1 is equal to z minus I times z plus I. And then we're evaluating this at z equals I. All right, now the z minus i's cancel, which is what we need when we do residue type problems like this. So those cancel, that's great. And then we are left with 2 pi I times what? Well, remember, we're evaluating at z equals I. So this is e to the I squared. And then on the bottom, we have I plus I, which is 2i. Okay, so 2 cancels with 2, I cancels with I, that's wonderful, and then I squared is -1, so what we have then is pi e to the -1, which is really just the same thing as pi over e. Okay, so what we just found out then is that this left-hand side is equal to pi over e. All right, that's great. Now let's go ahead and focus on this right here. What's going to happen there? Well, let's go ahead and go to a new page, and let's actually redraw our curve. So x-axis, y-axis, and then here, slightly better semicircle, maybe not really. All right, and then this is c, we're orienting this way, and the whole thing is gamma. All right, now we want to consider this integral here. Let's go ahead and consider that integral over c. So the integral over c of e to the iz over z squared plus 1 dz. Now notice, remember that c is just this entire arc. So how do we parameterize z on an arc? Well, it's supposed to be, if I drew it better, it'd be a perfectly circular arc up here. So we can parameterize by saying z equals re to the I theta, where theta goes from 0 to pi, right? Because we're traveling along in this direction here. So here's theta equals 0. We travel along the arc, and we get to theta equals pi. Okay, so 0 less than or equal to theta, less than or equal to pi. So then the integral actually becomes the integral from 0 to pi of e to the I re to the I theta over r squared, over r squared e to the 2I theta plus 1. And then what's dz? Well, if z is re to the I theta, then dz is ri e to the I theta d theta. Okay, so then dz becomes ri e to the I theta d theta. All right, now let's go ahead and focus on this piece right here and see how that simplifies. And actually, let's go ahead and do that on a separate page. So we want to look at e to the ir e to the I theta. Now remember that e to the I theta, so r and theta are both real. So this is e to the ir times cosine of theta plus I sine of theta. And then that's going to be e to the, so let's distribute the ir, and that's going to be ir cosine of theta. And then I times I is I squared, which is -1. So this is minus r from this r, sine of theta. Okay. And then let's go ahead and rewrite that as e to the ir cosine of theta times e to the minus r sine of theta. Okay, so remember that's this whole thing right here equals this right here. So let's go ahead and rewrite this as the integral from 0 to pi of e to the ir cosine theta times e to the minus r sine of theta. And then we have all over r squared e to the 2I theta plus 1, and then times r I e to the I theta d theta. Okay, now remember when we were talking about evaluating this, we were saying that eventually we want to take the limit as r goes to infinity. So what happens to this entire integral as r goes to infinity? Well, let's examine some of the pieces. And again, if you were actually doing this for a real homework assignment, you'd probably want to be a little more rigorous. But if we want to examine this as r goes to positive infinity, then what we can do is say, okay, let's consider the absolute value of this. Then actually I'm going to have to move to page 4 here. So we want to look at the absolute value of the integral from 0 to pi of e to the ir cosine of theta, e to the minus r sine of theta, over r squared e to the 2I theta plus 1 times r I e to the I theta d theta. Now the absolute value of that is actually less than or equal to the integral of the absolute value. And that's going to help us out quite a bit because that's actually going to make a lot of things go away in the sense that the absolute value of some of this stuff is just 1. Okay, so this is going to be the less than or equal to the integral from 0 to pi of the absolute value of e to the ir cosine of theta. And I'm skipping some pre-calculus type steps here where we're just using properties of the absolute value. e to the minus r sine of theta, and then times, let's say, ri e to the I theta over r squared e to the 2I theta plus 1, and then we still have d theta out here. Now, this equals the integral from 0 to pi of what? Well, this is actually just 1, because r and theta are both real. This whole thing is actually just 1, so that's nice. So that's 1, and then this is what? E to the minus r times sine of theta. We can actually drop the absolute values on that because this is always positive anyway. And what about over here? That's going to be r. And again, we can drop the absolute values on the r because r is always positive. We're taking a limit as r goes to infinity, so r has to be positive eventually, which it should be always positive anyway. But anyway, and then what's left? Well, we have absolute value of I e to the I theta. Absolute value of I is just 1, and then absolute value of e to the I theta, since theta is real, again, that's just 1. So this entire thing is actually just r. So then we just have the r over here. And then on the bottom, let's still say r squared e to the 2I theta plus 1. Now we could do a little bit to simplify this, but we don't have to worry about that, because now, remember, we want to analyze this as r goes to infinity. Well, as r goes to infinity, what's happening here? Let's ignore this piece right here that I just circled. Ignore that piece for now. Let's just go ahead and focus on r over this. As r goes to infinity, well, first of all, e to the 2I theta is going to stay bounded, right? Because theta goes between 0 and pi, and this is going to be bounded anyway. Plus 1 is just plus 1. Here we have an r, and here we have an r squared. So just think about what happens with r over r squared as r goes to infinity. Well, r over r squared behaves like 1 over r, and this goes to 0 as r goes to infinity, right? So all of this stuff right here, let's actually get rid of a lot of this circling here. All of this stuff right here that I'm about to circle in red, this is actually all going to go to 0 as r goes to infinity. Now, we're not quite done yet because we totally just ignored this part, but actually that's okay, because where does e to the minus r, whoops, e to the minus r sine of theta, where does that go as r goes to infinity? Well, remember, this is 1 over e to the r sine of theta, and remember, r and theta are both real. Now, as r gets really super huge, in other words, as r goes off to positive infinity, e to the r sine of theta is also going to become really super huge. And because theta is between 0 and pi, sine of theta is always positive, which is good. Okay, so again, theta goes from 0 to pi, which means sine of theta is always positive, which means e to the r sine of theta is always going to be, well, let's say r times the sine of theta is always going to be something positive. And as r shoots off to positive infinity, r sine of theta gets really huge, which means e to the r sine of theta gets even more huge, much more rapidly, which means this entire thing actually approaches 0. So everything in here approaches 0 as r goes to infinity, which means the entire integral actually approaches 0 as r goes to infinity. And remember, this entire integral is actually a bound for this absolute value here, okay? Remember, we took absolute values here so that we can more easily analyze this. So actually what that tells us then is that this integral here, if we go back to page 1, this integral here goes to 0 as r goes to positive infinity, okay? Because this integral here is actually less than or equal to the absolute value of the integral. I don't believe we mentioned that earlier, but this integral here is actually less than or equal to the absolute value of itself, right? And then what we just saw was that the absolute value is actually less than or equal to something that goes to 0 as r goes to infinity. Therefore, since this always has to be positive or 0, this must also go to 0 as r goes to infinity, which gives us the result that we just said here. This entire integral goes to 0. Okay? Now let's go ahead and summarize everything we have so far. So starting from this equation here, all right, let's see what we have. Let's go back to page 5. Now we have the integral over gamma of e to the iz over z squared plus 1 dz equals the integral from minus r to r of e to the ix over x squared plus 1 dx plus the integral over c of e to the iz over z squared plus 1 dz. Now what I want to do is take the limit of both sides as r goes to infinity, but actually first, remember this was equal to pi over e, right? That's what we saw on the first page here. We got pi over e when we evaluated using residues. So we end up with pi over e equals the integral from minus r to r. Now what I want to do is rewrite e to the ix as cosine of x plus I sine of x over x squared plus 1 dx. Now this, remember, this just goes to 0 as r goes to infinity. So, as r goes to positive infinity. Now this integral itself is not 0 always, it's just 0 as r goes to positive infinity. And because we're eventually going to take a limit as r goes to infinity, then this is just going to be 0. So actually, let's just go ahead and take the limit of both sides now. Limit as r goes to positive infinity. All right, so we have that going on there. And plus the limit as r goes to positive infinity of the integral over c of e to the iz, e to the iz over z squared plus 1 dz. Okay, so like we just explained a couple times, this equals 0. Now that we're sending r to infinity, we're taking a limit as r goes to infinity, so this is now 0. All right, if we take a limit as r goes to infinity of pi over e, of course we still just get pi over e, because it's just a constant. And then what happens over here? Well, here we end up with the integral from minus infinity to positive infinity of cosine of x over x squared plus 1 dx plus I, that's an I, times the integral from minus infinity to positive infinity of sine of x over x squared plus 1 dx. All right, so notice what I did here was I had cosine of x plus I sine of x. I split this up into two fractions, and then I split it up into two integrals. Now what we have is pi over e equals these two integrals being added together. So to evaluate this, this and this here, what we do is we equate the real and imaginary parts. So to have more room, what we have here is pi over e plus 0i equals the integral from minus infinity to positive infinity of cosine of x over x squared plus 1 dx plus I times the integral from minus infinity to positive infinity sine of x over x squared plus 1 dx. So equate the real parts and the imaginary parts. Here's the real part of the left-hand side. Here's the real part of the right-hand side. Here's the imaginary part of the left-hand side. And then here's the imaginary part of the right-hand side. So remember, the original integral we wanted to evaluate was just the integral of cosine of x. But as a special bonus, through this process, we actually also evaluated this one. And what we see then is that the integral from minus infinity to positive infinity of cosine of x over x squared plus 1 dx equals pi over e. Right? And that is our final answer there. So this has been an example of using contour integration to evaluate a definite integral, and I hope you found this video helpful, and thank you for watching.